Okay guys, so we're going to talk about area in a plane. This is section 8.2 of your textbook, and your textbook does a very good job of laying out these problems. It also goes through like some thorough definitions and writing those definitions using notation. And so feel free to look back there if you want an additional resource to this video. Okay, so your learning goal for today is that you will be able to apply the definite integral to solve problems involving areas. Okay, so there you have it. That's your learning goal. So there are 3 different cases you need to consider when we're looking at these types of problems. And the first type, case 1, is area between 2 curves. Now, you've actually already done this before, you just haven't really thought about it this way. So like when I give you any sort of curve f of x, and I tell you to find the area under f of x, you're looking for the area between the curve and the x-axis, right? Well, the x-axis has an equation. That equation is y equals 0. So you actually have been finding the area between 2 curves before, but now we're going to look at curves that aren't necessarily the axis, okay? So that's what we're going to do now. So for the first example, we want to find the area of the region between the curves y equals x squared plus 3 and y equals negative x squared plus 2. So I'm going to go ahead and graph these now. It's always a good idea to graph your curves, so that way you have a picture of what's happening, right? If you can't visualize it, it's going to be hard. So I'm going to graph this first curve in green, this y equals x squared plus 3. So that's a parabola that starts at 3. And it'll look something like that, assuming it actually went through 3. There we go. And then I'm going to graph the other curve in purple. So it's also a parabola, but it starts at 2, and it's opening downwards, right? Because their parabola, or the sign in front of x, is negative. Okay, now hopefully your curves look way prettier than mine. That's like my expectation, that you can draw better than I can on an iPad. And I want to go from -1 to +1, okay? So if you think about it, you're looking for this region right here, okay? Which, I don't know, I'll make that another color. Let's call that color yellow, okay? So that's the region we're looking for. So pretend, for example, you did not have the purple curve, okay? If you were looking for the green area, you would be looking, whoa, that's not what I want to do. Can I erase it? Nope, okay, whatever. So if you were looking for the area just under the green curve, you would be looking for this entire region here, right? Which is the integral, as we know, from -1 to 1 of that first curve. Okay, now we need to subtract the area then under the purple curve, right? Because we don't want it there. We just want the yellow region. So we need to subtract that integral. Okay, so that's what we need to do. Now, let's see if I can erase this x-axis so I have more space. Now, I wrote them in 2 integrals here because it's really easy to kind of look and see what's happening, but you're also, it's completely correct if you write it as 1 integral, okay? Right, think about your integral properties. Normally, like, you'd pull it apart if you're subtracting. In this case, we can even put it back together. So this is the same thing as the integral from -1 to 1 of x squared plus 3, right, from my green curve, minus the area for my purple curve. So minus negative x squared plus 2, all with respect to dx, okay? And then you can go ahead and combine some like terms here to make your life easier. So if we were to combine our like terms on the integral, we'd go from -1 to 1, and then we'd have 2x squared plus 1 dx, okay? And we can go ahead and just integrate those terms. Okay, now you are capable of integrating and I'm out of space. So you need to fill in whatever that is. Okay, so take your integral and integrate it. Okay, so then that's the first case, okay, between two curves. And normally you say, let's see if I can find more space. Hang on. So the way your book has it written, which is correct, is if we say this is your top curve, f of x, okay, and g of x is your bottom curve. And you have to know that f of x has to be bigger than g of x. Then you can integrate from your endpoints, or your bounds from a to b, of f of x minus g of x, right? Because that's your bottom curve, all with respect to x, okay? So you can think of that also, right? Which is exactly what we did. We took our top curve, right? We took your green curve, integrated it, subtracted it from the purple curve, okay? It's exactly the same thing. So let's go ahead then and move on and look at what happens when instead of between two curves with a given bound, the bound is formed by the fact that our curves are intersecting. Okay, so we're going to look at regions now that are formed by intersecting curves. Okay, notice these curves up here don't intersect, these ones will intersect. Okay, so we're going to start, so example 2 says, find the area of the region enclosed by y equals x to the fourth and y equals x. So again, let's start by graphing it so we can figure out what's happening. So x to the fourth is a parabola, or it's not really a parabola, but it has that parabolic shape. So it'll look something like this. It's a little bit wider than a parabola. No, it's the opposite. It's a little bit more narrow than a parabola, my bad. And then y equals x looks something like that. Okay, so we're looking for the area that's pretty small here, but of this little intersecting region. So let me do that in green. So we're looking for this area. Okay, now, if we're looking for that area, we need to think about what our bounds are. Okay, so our bounds are now determined by where our curves are going to intersect. Okay, whereas up here, in this example, I gave you the bounds. Now you're going to have to figure out those bounds for yourself, but luckily this isn't very hard. Okay, especially if you have a graph in front of you. So, first of all, it should be super obvious that these start by intersecting at 0. Okay, that should be fairly obvious. Now, if y equals x, that means like when y is 1, x has to be equal to 1, right? When y is 2, x has to be equal to 2. So think about your power. The only time that's going to happen with that sort of function is at the point 1, comma 1. Right? Because 1 to the fourth is 1. So you should be able to do it like that. The other way you can do it too is using the intersect feature in your calculator, right? If you graph both these in your calculator and do second calc, one of the options is intersection, okay? So that's what we're going to integrate to now. So we're going to integrate from 0 to 1 here, and we're going to apply the same principle we applied before. So for our integral from 0 to 1, we're going to use the curve that's on top, right? So we're going to assume we have this whole purple region we're going to integrate, and then we're going to subtract off the region under x to the fourth that we don't need. So we need everything under x, but we're going to get rid of this extra piece, right? That extra piece underneath your parabola looking thing we got to get rid of. So we're going to subtract it from x to the fourth, and again, we're going to integrate it with respect to x. Okay, so same thing, our top function minus our bottom function. Okay, should be pretty simple, right? You're getting rid of the piece you don't need. The piece you don't need stops at your bottom function, so that's what you're subtracting off. So when you integrate this, you're going to get 1/2 x squared minus 1/5 x to the fifth, and you're going from 0 to 1. So that's going to give you 1/2 times 1 squared minus 1/2 times 1 to the fifth minus, if you plug in 0, you're just getting 0. Okay, so I don't know what a half minus 1/5 is off the top of my head, but you guys can figure it out. Okay, simplify this, fill in what goes in there. Okay, next example, example 3. That's not what I meant to do. I think where's the right button? There we go. Example 3. So same thing, we're looking for the region formed by lines that are, or curves that are intersecting. Okay, so this says find the area of the region in the 4th quadrant, okay, bounded by y equals negative the square root of x and y equals negative x plus 3. So let's go ahead and graph them as always, and we only care about the 4th quadrant, so I'm just going to draw the x-axis up higher so I can, work with the space I'm given. So when I want to look at y equals negative the square root of x, I'm going to do that curve in green this time. So that curve starts at 0, 0 and looks something like that. And y equals, oh, of course, negative x plus 3, and I didn't draw my graph up high enough because I wasn't thinking ahead. So plus 3 we'll say is up there. So if I do that one in purple, it'll probably come down looking something like that. Okay, so we just care about the 4th quadrant. I don't care at all what's happening above my x-axis, right? Because this is the 4th quadrant. 1, 2, 3, 4, counterclockwise. This is your 4th quadrant. That's all I care about. Now, if you notice, this example, example 3, kind of puts together the two ideas we talked about in examples 1 and 2. Because if you're looking at this picture, our bounds are based on two different things, right? They're based on when the two curves intersect here, but also when we're hitting the x-axis here. So we have to think about the whole picture together. So when you're doing problems like this, the easiest way to do it is to separate, or how you want to do it, is you want to separate the two curves. So if you think about it, like this region right here is formed by different curves than this region here. Okay? So that purple region uses both the curves you're given, whereas the green region only uses one of the curves. So because we're in a situation where we're using two different curves and one curve in one part of my integral and two curves in the other part of my integral, we're actually going to have to count for both of these areas separately. Okay? So we're going to have to figure out then where y equals negative x plus 3 crosses the x-axis. Because where this curve crosses the x-axis, that's my bound that I'm looking for. So let's figure that out. So it crosses it at 3, which shouldn't be that hard to figure out, right? If you plug in y equals 0, you'd get 3 for x. Okay, so it crosses it right here at 3. So when I set up my integral then for the green curve or that green area, I want the integral of, again, just that green area. So I want from 0, because that's where my green area starts, to 3 of just that one curve, which is negative the square root of x dx. Okay? Ignore this 1. I don't know what this thing is doing here. Ignore that. That's not part of anything. Okay, that's just a mark. So that integral right here will calculate the area of just this green region, and now we're going to have to figure out the integral that's going to calculate the area of just my purple region. So I'm going to do that integral in purple. So now our integral is going to 3, but we don't know where it's ending because it's ending where these two curves are intersecting. So you should do second calc in your calculator to find that point. Remember, you need 3 decimal points. And that point where those two curves intersect to 3 decimal points is 5.303. Okay, so let's look at that section carefully to figure out which curve we're going to subtract from the other. So let me zoom in for a second and grab some more colors happening here. Okay, so this curve right here on my x, this is the square root curve, right? Negative square root of x. So if I were to calculate the curve, the area under that curve, I'd go all the way to my x-axis. Okay? Now, if you were to just look at the purple region, which I don't want to do in purple because we've already done it in purple. I don't know, so let's do it in red. So if you were to look at, sorry, that's not the right line. Just the area under the curve of the line going to the x-axis, it'd be that. Okay? So we're going to have to subtract the x curve here, or the y equals x line from the other curve. Okay? So even though we say it's the bigger curve minus the smaller curve, it's really the curve that's causing the most area. Okay? So in this case, negative square root of x is technically smaller than y equals negative x plus 3, but it doesn't matter because we want to look at terms of actual size of area. So when I do that, then those are the two curves I'm going to subtract from each other. So I'm going to subtract negative the square root of x minus negative x plus 3. Don't forget to put that whole thing in parentheses, and I'm doing it all with respect to x. Okay, now you guys are perfectly capable of integrating those things, so you should do it to come up with your answer. Okay, so whatever answer you get here needs to be added to the number you get there. Now, as a hint, this entire region is below the x-axis. So if your area is not negative, something went awry. Okay, the entire region is below the x-axis, so you need to make sure that your entire answer is negative. Okay, so we are going to integrate now with respect to y. Okay, so I told you, it says draw a cross section or rectangle that is either horizontal or vertical so that it will intersect both curves for the entire region, okay? Make sure it works for the entire, why is this not working? Entire region, okay, the whole thing. So if the cross section is perpendicular to the y-axis, you should integrate with respect to y. So let me give you some examples. Here's a curve. So here's one curve, here's another curve, okay? If you're drawing rectangles in this region, if you draw a vertical rectangle, so pretend my line's a rectangle, it's not intersecting either curve, right? But if you were to draw a horizontal rectangle there or here or there, it would intersect both curves, and notice it's perpendicular to the y-axis. Okay, so another example. Okay, if those are your two curves, you can draw vertical rectangles for sure, but look what happens. That rectangle is no longer intersecting both of my curves. If I were to draw it the other way, horizontally, it would intersect both in the entire time, right? So when that happens, when you can draw a horizontal rectangle that intersects both your curves, you want to integrate with respect to y. So we're going to look back at example 3 and redo it, but now we're going to integrate it with respect to y. Okay, so let's do that. Wish there was a way to cut and paste my pictures. Not that they're pretty pictures, but you know. Okay, so we're drawing negative square root of x in blue. So negative square root of x, and we're drawing negative x plus 3 in green. Okay, now, what we did before is we broke it up into two areas, right? So we broke it up right there, and we integrated this side, and then we integrated this side, and we did it separately. What we're going to do now is we're going to integrate them together, but with respect to y. So if you notice, I can draw like a horizontal line here that goes through both my curves, and no matter where I move that line, it's going to go through both my curves for the entire region in my fourth quadrant. So if I'm going to integrate with respect to y, the first thing I need to do is solve both those equations for x, because you want to plug in y-based equations. So let's look at the blue one together, okay? So right now you have y equals negative the square root of x. So the first thing you need to do is get rid of that negative 1. So you're going to end up with negative y equals the square root of x. Okay, now you need to get rid of the squared. So you need to square both sides, okay? So you're going to end up with y squared is equal to x, okay? You don't need to worry about the negative because negative y times negative y is y, positive y squared, okay? So you don't need to worry about it. So we're going to use this equation for our blue curve. Let's look at the green curve. Okay, subtract 3. Y minus 3 equals negative x. Get rid of that negative. So negative y plus 3 is equal to x. So those are the two equations we're going to use. Now, we're looking at area to our y-axis. Okay, we want to go all the way to the y-axis. So we got to figure out what curve is going to be subtracted from the other. So if I zoom in, okay, if I'm just looking at the area of that green line to the y-axis, because I'm with respect to y now, it would go all the way here, right? It would go all the way to the y-axis. So that's the area of the green curve to the y-axis. The area of the blue curve to the y-axis is this, okay? So the blue is the extra. So that's what we got to subtract. You got to subtract the extra, the piece you don't want. So when you do that, because I'm integrating with respect to y, I'm going to get y plus 3, because that's the bigger area, minus the smaller area, y squared, with respect to y, so I'm going to put in a dy. Now, you need to figure out your bounds. So it's pretty obvious that this bound right here is 0. Since it's at the top of my curve, right, that's the highest point of the area, that's going to be my upper bound. Now, this point right here, you should figure out that point of intersection, and maybe it's still in your calculator, but that y value of your point of intersection is negative 2.303, so that's going to be your lower bound. Okay, so go ahead and integrate this. You're capable of doing it to get your answer. Do not fill in your summary. Okay, make sure you write down any questions you have.